All right, so let's look at the next section. If we go in order, we're looking at 5.3, which is inverse functions. So I guess we should start with the definition of what inverse function is. Okay, so section 5.3, inverse functions. Okay, so the main definition, there's two ways to think about it, and it's going to be equivalent. And the definition, not of inverse, but really the definition of the condition to have an inverse, is something called a one-to-one function. So one-to-one function. Okay, sometimes we write it like that. So the first way of saying it or thinking about it is that every output is a result. So every output is the result of exactly one input. Every output is a result of exactly one input. And we're gonna have a little picture to make this more clear. And the second is in terms of a condition. So it's equivalent to what we just said. And if we look at different outputs, so if A is different than B, then the output f of A has to be different than the output f of B. So in other words, different inputs should have different outputs. That's exactly the same thing as the first one. So if we want to look at a little picture, so let's say usually we use it's called a sign diagram. I'm sorry, arrow diagram. So we draw these little circles here, and then I'm just gonna make up some numbers: -1, 0, and 1, let's say. And then so this is the inputs, obviously, and these are the outputs. So let's say this is 1 and 0. All right, then the way I'm gonna draw my little arrows, so let's say this one goes there, this one goes over here, and this one goes over here. So this one, you can see that this is not one-to-one. So every output should be the result of exactly one input, and the one that is messing it up is right here. These two have the same output, and that's not going to work for this to be a one-to-one function. So if we want to look at the second condition, so let's say this is A right there, and this is B right there. So obviously A is different than B, so they should have different outputs, right? So then f of A should be different than f of B, but obviously they're not, they're the same. So that's one way we can think of the definition of one-to-one function. Okay, so why is it that a one-to-one function is important? Well, back in your pre-cal days, there was an important fact is that for a function to have an inverse function, the condition is it has to be 1-to-1. So then let's say if we recall the fact, we say that a function is invertible. In other words, it has inverse function, is invertible if it's a 1-to-1 function. Okay, so that's the condition. If it's 1-to-1, then it's going to have an inverse function. It's invertible. Okay, so that's the way we looked at it from the point of pre-calculus. From the point of calculus, we have something called monotone functions, and that's going to be the condition we're going to use. All right, so I guess the next topic we're going to talk about is monotone functions. Okay, so what is a monotone function? So a lot of times we emphasize this by saying strictly monotone. And what it basically means is that it is either increasing. So I guess I could call this its definition. It is either increasing or decreasing. Or decreasing. Increasing or decreasing. Okay, so if that's the case, that is strictly increasing or decreasing, and that is supposed to be a sufficient condition for it to be invertible. Let's see by the picture if that turns out to be the case. And let's use something that we've been working with recently, e to the x. So then a good example is y equals e to the x. So let's bring in the little picture. And whenever you want to talk about inverse functions, we think of it in terms of a reflection. You use a line that is at a 45-degree angle, and we're gonna do a reflection at a 45-degree angle. Okay, so let's see if I have the ability to do a dotted line. It doesn't show up here. All right, so let's just do green. So then it's a line at a 45-degree angle. Okay, and that's called y equals x. And we're going to reflect it. So what does e to the x look like? Well, let's put that one in red. Well, let's use blue. So there's e to the x. And then if you reflect it, then it's going to land on the opposite side. So let's put that one in red. So then it's going to look roughly something like this. And when we do that, we get the inverse function. So in other words, the result of reflecting is f inverse. Okay, and who is f inverse? Well, that's ln, the logarithm with base e, ln of x. All right, well, looking at it, e is increasing function. E is an increasing function. And it's always increasing. So that means that when you flip it, in other words, when you do the reflection, it's going to have an inverse function, and it sure does. So if you look at the blue one, and if you do the reflection, you get the red one, and then you get another one that also happens to be increasing too. So it works out pretty nice. So then this guy right here is an increasing function, and we got the inverse. Okay, so this clearly works. But if I'm gonna convince you that this is a sufficient condition, that it has to be monotone, in other words, either increasing or decreasing, not both. This is implied, but I guess I'll write it, not both. Let's look at another picture. Well, I guess let's write the little fact or the rule that we're using. So before we forget, fact, a function has inverse, in other words, is invertible. Is invertible whenever it is strictly monotone. Okay, so that's basically the idea. All right, so again, let's look at another picture, and then let's see how it works out in this case. Let's pick on a parabola, y equals x squared. So everybody knows what that guy looks like. All right, I guess let's put it in blue. And if we're gonna do our reflection, we need to use the 45-degree line again. Let's go back to green. So then if we do it at a 45-degree, I'll make it dotted this time. And then if you flip it, do the reflection, what we end up getting, so I'll do it on this side. So let's go put back our little green line again. So this one requires a little bit of imagination, but if you flip it, it's gonna face to the right, or open to the right if you want. Well, let me do that again. That way I can make a nice smooth picture. Okay. All right. So this, what we got was the inverse, but it's not a function because it doesn't pass the vertical line test. So yes, it has an inverse, but it's not an inverse function. So then here, we're going to say that this, after we flip it, is not a function. In other words, it's not invertible because it doesn't work anymore. And why didn't it work? Well, was this guy monotone? No, it wasn't, because here it's decreasing and then increasing. So that's why it didn't work, because this one was not strictly monotone. So then you can think of it in terms of two conditions. If you use the pre-calculus condition, you can say that it's not one-to-one. So then this guy was not one-to-one. So that's why it wouldn't work. And if we use the calculus condition, it's not strictly monotone. And it didn't work for that reason. Okay. So there's something called restricting the domain. And what that means is, if you take a piece of the graph, not the whole graph, maybe with this new restriction, you will be able to get a graph that is invertible. So the way this one is working, the original parabola, since it has a piece that is decreasing, then a piece that is increasing, what if we just consider one piece of the parabola? Will that be enough to make it work? So that's what we're going to investigate. Okay, so let's do this. Call it example number 1. And then let's say, as my example, it'll be the square root of x minus 1. Okay, so a good place to start is looking at the domain and range. Okay, so looking at the domain, this is the square root function. So it looks like half of a parabola that opens sideways, if you remember the parent functions. So I guess recall. And I'll do just a little mini version over here. All right, that didn't work out. Let's try to make it a curve. There we go. So that's the parent function. But then if you look inside the radical, in here, the -1 tells you that you're shifting sideways. But inside, when you see the -1, you're not going to go to the left, you're actually going to go to the right. So again, you have to remember your pre-calculus rules for transformations. So this is 1 unit shifted to the right. So then we will say this is 1 unit shifted to the right. So then if that happens to be the case, so let's say, let's call this 1, then the graph is really over here. So then looking at the domain, it starts from 0. I'm sorry, from 1. The original one started at 0. This one starts at 1. From 1 all the way to infinity. All right. Now that we have the picture there pretty handy, let's go ahead and talk about the range. So the range of the y values What is the lowest y value? Well, it starts from 0 and it's going to keep going up forever. So even though it doesn't look like it's going to keep going in this direction forever, it does. It's moving slowly, but it's going to keep going up and up and up. If you keep moving to the right, this one keeps going up and up and up. So then this should be from 0 to infinity. And this one was from 1 to infinity. Okay. Now, how is it that we find the inverse of anything? Well, you do a switch. So then, well, I think I can do it over here. How to find inverse? You switch the x and the y in the equation. So then, to find the inverse, if I switch things, instead of the y value, it'll be the x. So it'll be x and then square root y minus 1. Okay, but then we have to solve for y. So you would square both sides. So then square both sides, and as a result, you get x squared, and then it cancels on this side, so you have y minus 1. And then if you add 1 to both sides, you're going to get that y is x squared plus 1. Okay, now I don't like when it's written backwards, so let me just fix that really quick. Y x squared plus 1. All right, but then you're going to think, well, this is a parabola, and a parabola didn't really work. Well, let's look at the picture. So I guess we can do it over here. Let's see. If you graph this, this is a parabola that is shifted 1 unit up. So because of the plus, this parabola is shifted 1 unit up. So then it's going to be at 1. So let's see a different color. Let's go with green. So let's say this is 1. Then my parabola should look something like this. But why is it that they're not matching up according to the reflection? Because if you remember, this guy in blue, that is representing f. So this is f right there. That's the graph of f. And if you do the reflection, it's supposed to give you the green one. All right, so let's get rid of the red one, since that one, oops, I got rid of the whole thing. Okay, so let's see, this one was right there. And then if you do the reflection, I guess we need the 45-degree angle line. So if you do the reflection, you should get a piece that is like that. Well, why didn't it work? Well, after you switch and solve for y, you're supposed to switch the domain and range. So guess what? We're not done here yet. The next step is to find, for this guy, find its domain and range. So then the domain And then the range will actually be very easy. You just switch. So this is gonna be from 0 to infinity after you switch it, and then you get the range by switching it over here. In the original one, it was 1 to infinity. So then that's telling me that when I look at the graph of my parabola, the x values are from 0 to infinity. What does that mean? That means that this is really not there. And then the range is from 1 to infinity. That's still true. From 1 right here, it keeps on going up forever. So then notice that now it does match, that this inverse is in fact the inverse after you reflect it. That's because the domain was restricted. This little part that we scratched out, this is removing part of the graph. In other words, part of the x values. So now it does work if you have this restriction in place. Okay, so hopefully that is a it serves you as a reminder how to work with inverse functions. So this was, I guess, like a little mini review of inverse functions. All right, so now let's go back to calculus. The derivative of inverse functions. That's really what we want to, I guess, focus our attention on. Derivatives of inverse functions. So this is what we want to accomplish. Take the derivative of any inverse function and it turns out that it's pretty weird looking formula, but it's not too hard. It's just, it looks harder than what it actually is. It's the reciprocal of the composition. So f prime and then f inverse. So then be careful. Okay, so if you don't remember what this function inside of another function, it's called composition. And it's f of g of x was f of g of x. All right, so that's really what's going on here. It's composition. Okay, so let's see it in action. And then let's use an example of something that we've worked with already. So let's say ln. We know what the derivative of ln is already. We were able to figure it out without having to use this information with inverse. But if you had this inverse, would actually make it easier. All right, so anyways, let's go back. So the derivative of ln, it was 1 over x. Okay, so let's just leave that there for now. And if we're gonna use our new little formula over here, let's just keep track of the things we're gonna need. So we know that ln is the inverse of somebody, right? So this is what we know. ln is an inverse function, but it's the inverse function of whom? Well, it's the inverse of e. So in other words, f of x is e to the x. We know that relationship. They're inverse of each other. But what do we know about the derivative of f? The derivative of e to the x, this is the easiest one to remember because it's really the same thing. It's e to the x. Okay, that's good to know. So let's go ahead and plug things into our new formula. So then it's going to be the derivative. And then in here goes the inverse. Who is the inverse? Well, we just said that the inverse is ln. So that's what goes in there, ln of x. And it equals 1 over the composition. So in other words, notice that the inverse is inside of the derivative. So then the inverse is inside of the derivative means that I'm going to have to take the inverse, which is this guy, and plug it inside of the derivative, which is in there. What does that look like? Well, let's plug it in. It's going to be e, and then instead of x, you're going to plug in ln of x. E ln of x. Well, e and ln cancel. So that's going to go away. Gone and gone. So what do you have left? 1 over x. And that's what we had said. So check mark. We get the same thing. Okay, so it works out like it's supposed to. All right, so now that we know that it's been verified, it works pretty nice. Let's work on an example. So I think I'm on example number 2. So let's call it example number 2. And let's pick on the parabola again, x squared. All right, but if we're gonna be talking about the inverse, we have to be careful. In general, it's not invertible unless you restrict the domain. So let's say that on the interval from 0 to infinity. Okay, all right, so what does that mean? Well, let's look at the picture. So then the parabola is not the whole thing. The parabola is only half of a parabola starting at 0. So in other words, over here I'll make it dotted, but then the piece that we actually are talking about is this piece right here. So that means that it is going to be invertible, because if you do the reflection, then we're going to get a square root. So again, pretending that you did a reflection using the 45-degree angle line, you're gonna end up getting this guy over here. So if this is f, whoops, if this guy is f, then this guy is f inverse. Alrighty, so f inverse is y equals to the square root of x. Okay, that looks pretty good. So we're gonna take the derivative and we're gonna need the derivative of the original function, and then we're gonna do composition. So all of these things we're gonna use because it goes back into our new formula for derivative. So I guess I'll put it over here. The derivative of the inverse was 1 over, and it was composition, prime, and inverse. So the inverse goes inside of the derivative, in other words. Okay, so we're gonna need to know, we already have the inverse here. So in other words, this we already have, it's there, that's the inverse. Okay, so it's this guy. And then the derivative is still missing, so I guess let's take the derivative. So other things we need. So the derivative of x squared, since that's the one we're looking at, is 2x. So then what is this saying? This is saying that the inverse is going to go inside of the derivative. So the inverse goes inside of the derivative. So here's the inverse. It's going to go inside of the derivative. So it goes in there. All right. So let's give it a shot. All right, so then the derivative of the inverse, which is square root of x, is equal 1 over, and then we said the inverse goes inside of the derivative, and that's what I have over here in the yellow. So then, in other words, I need to plug it in right here. So then it's going to be 2 multiplied with the square root of x. So it'll be 2 multiplied with the square root of x. So that's supposed to be my answer. All right. Well, we can easily check. All right, so if you want to take derivatives directly, so derivative, instead of square root of x, this is x to the power of 1/2, if you remember. And when you take the derivative, you multiply, and then you subtract. So in other words, you're going to multiply 1/2 x 1/2 minus 1 is going to be negative 1/2. So negative 1/2 goes there. But you don't leave it as a negative 1/2, you bring it downstairs. So 1 over There's already a 2 down here. This becomes 1/2. In other words, on the bottom, 2 square root of x. And yep, it works. So now, the benefits, we're not seeing the full benefits of the formula yet. Obviously, these are easy derivatives, but a lot of times it's like a little going through the back door. If it's difficult, because in general, I should say that the inverse functions in general are kind of hard to find. So if we can go through a back door, sometimes that's a big benefit. So this connection works out pretty good. All right, so let's see what else we can discover about the derivative. So there's a nice property. And the relationship is that f and f inverse have reciprocal slopes. Reciprocal slopes. And slope here is keyword for derivative. Okay, have reciprocal slopes at reflected points. All right, so how does that look? So let's pick an x square. Y equals x square. And we know, let's do half of the parabola. So if we restricted the domain, so pretty much the same scenario right here. The blue graph and the red graph. So this one was square root of x. Okay, and we need reflected points. All right, so let's say this here is gonna be 2, and this point up here would be 4. All right, compared to this one, if this is 4, then this would be 2, because the square root of 4 is 2. So these are reflected points. So then if you want, let's label the little point here. This is 2, 4, compared to this guy over here, 4, 2. And we're going to talk about slopes. So that means that we have to invoke the tangent line. That didn't come out too good. Let's try it again. Okay, and then the tangent line over here. All right, so it looks like it's not gonna take it very good. So let's just leave it like that. All right, so let's see what the slope is here. M equals, how do we calculate the slope? Well, that's what the derivative does. So then the derivative here, y prime, let's call it, it was 2x. The derivative over here, y prime, was 1 over 2 square root of x. And if you have the x value, you just plug it in. And we sure do. Here's your x value. So then here's your x value. We just plug it in. And it goes right here. So it's going to be 2 times 2. So then the answer is 4. And then over here, if you plug in the 4, 2 square root of 4. So then that's going to be 2 times 2, 1/4. So are they reciprocal slopes? Let's see this guy right there. And this guy right there. So yep, they're reciprocals. So then that only works if they're inverses and if they're reflected points. All right, so let's go to the last one. Let's see, what example am I on? Example 3. So 2x, and then cosine of x. So part A. Find the slope of the tangent line. So for both of these, we're going to do the same thing. Find slope of the tangent line. Basically means it's invoking the derivative, so we're going to have to take the derivative. That's exactly what it's saying. So part A is going to be at x equals to 0 for f of x. And then part B at x equals to 1 for f inverse. All right, so let's do part A. Okay, so if x equals to 0, what point are we talking about? So that means to find the y value, we need to plug in x. So y is going to be f of 0. So 2, plug in a 0. Cosine, plug in a 0. So the first one is 0, but cosine of 0 is 1. So this is 0, but cosine of 0 is 1. This guy is 1. So then if we equal 1 here, my point is going to be 0, 1. Okay, so now that we have the point, let's go ahead and invoke the derivative, because that's how we find the slope of the tangent line. By definition, the slope of the tangent line is given by the derivative. So let's go the derivative of the function. Pretty easy. The derivative of 2x is just 2. And then the derivative of cosine is negative sine. And then if you want to know the slope, you just plug in your x value. So then it's going to go in there. So it will be 2 minus sine, and the x value was 0. And sine of 0 is 0. So it looks like this answer is 2. So this is 0. So then the answer, it doesn't like red for some odd reason. Let's try this one. All right, well, there you go. I guess it automatically crosses it out. Anyways, the answer is 2. Okay, so that's good. That's the answer for the first one. All right, let's take care of part B. So we'll do the same thing. We're going to have to invoke the derivative of the inverse. The problem is, who is f inverse? So let's go back, and if you look at the original, so this guy right here, 2x plus cosine of x, if you want to find the inverse of it, then you have to talk about arc cosine. Let's try to avoid it. What do we know about it? Well, if they're the inverse, it's going to have reciprocal slopes at reflected points. All right. So what is the reflected point? Reflected This is not working out for me. Let's try it again. Reflected point is gonna be 1, 0. And at this reflected point, it's gonna have a reciprocal slope. In other words, that's the derivative. So the reciprocal is going to be, well, look at there. You had the 2, so it's just 1/2. So we were able to take the derivative indirectly because we knew the relationship that the relationship that they have reciprocal slopes at reflected points if they're inverses. So there you go. Okay, so that's going to take care of section 5.3. So now we're ready to do, I think what I'll do is I'll make a separate video for each section. That way every video doesn't have to be too long. So I'll go ahead and stop right here. I'll post this one and then I'll do the next video, which will be section 5.4. And we're going to be working with E. All right. So let's go ahead and do that.